Okay, guys, let's start the lecture. As you see, we will now continue with a new chapter. This one is about photopolymerization processes. We will be using some special materials called photopolymers, like this one here. This is a photopolymer, and the thing is that we will see once they are actually irradiated, you will have some chemical reactions started and they will be solidified. Initially, they are in liquid state, but after the printing, obviously, we need to have them in a solid state. And in this chapter, we'll be discussing some processes based on photopolymerization, like SLA, DLP, CLIP. So there will be at least 4 to 5 of them. And I would like to briefly start with the advantages of this method. And the main advantage is the high accuracy of these parts. You can produce very small products having detailed features. Another issue, you can have different materials by adding little, let's say, material components inside these mixtures. You can have tough materials, flexible materials. So this is a nice advantage of photopolymerization processes. Another thing, you can use the same material for support and builds. You don't need to have a special material like in the case of triple F. In triple F, you have both options. You may use the same support structure or you may have a different material. But this one might be considered as a disadvantage depending on your application. Another thing, you can produce very watertight models, very small features can easily be produced. Another thing, you can produce very clear shapes, transparent parts by using proper material, or this one is actually preferred in medical industry a lot. You may have some medical materials and you may have some replicas of different parts. And what are the disadvantages? After the printing is completed, I will discuss some other details in the upcoming slides. You may need to do post-curing. So once the part is printed with this material, you will take your part out of the printer and do some extra curing operations so that its properties will be much better. Another issue, if you do curing in a wrong way, you may have more warpage, distortions on your parts. Another issue, it's quite brittle as opposed to triple F or other 3D printing processes. You can easily break your part into smaller parts. And since the technology is again layer by layer, you need to have support structures, especially for shallow angles. Another issue, another disadvantage is that these materials might be sometimes toxic and they're always light sensitive. For instance, I cannot use this one on the printer since it's already under the sunlight or room light. So I cannot use it in printing. Otherwise, it will not be cured. It will not be solidified. Some portions are, you may see some particles there. Some portions are already solidified. So these are the disadvantages, but it has also, as we mentioned, great advantages. So especially for very small and detailed parts, people prefer to use such photopolymerization processes. So what we need to do, we need to have actually a light, a kind of a light source and photopolymers. And we may put these photopolymers into some kind of a vat so that you can easily reflect some light or some laser or different, like this one, UV light, so that some radiation will be on the parts, on the material, and we will start some chemical reactions. And with the help of these lights, after the chemical reactions are started, this liquid material will be solidified, and we call this simple reaction as photopolymerization. And it started around 1960s. But the thing is that people were not using this method for 3D printing. They were just using it for coating the surface of some special products or printing some textures on paper on different materials. But they were not using it for 3D printing. And Another thing we know about this polymerization is that dentists actually are using it a lot. If you are gonna do any filling into your teeth, then they put such resins, such photopolymers into the openings, and then with the help of UV light, they cure it and try to solidify that material in between your teeth. Now I would like to show you a test case and mass customization example. Yes, this is Gillette company, and they are using this process, stereolithography, to produce actually customized holders for their Gillettes.
We make razors for millions of guys around the world, and we know one size doesn't fit all. We wanted to do something new, unique, and personal, enabling people to create and personalize their own razors. The moment we realized that, Razor Maker was born.
So this is actually the type of printer right now. In a moment, I'm going to describe you. This is an SLA printer, and it's from Formlabs, and they use the same printer to print such customized products. A product which is actually specially designed for you.
Razor Maker is super exciting because we're giving thousands of people the chance to create a razor that's in their own, that's unique to them, to open up an entirely whole new world of possible razor designs. And then it's shipped directly to their door. Creating something truly different means working with great people and pioneering technology. We're just starting, but it's a fun ride working with our Boston neighbors at Formlabs who are at the cutting edge of 3D printing.
Our vision was always to make 3D printers as accessible as possible in order to bring the technology to as many people as possible. We see the potential.
And the thing is that if you look at these actually holders, they are quite detailed. They have very small features, and the only additive manufacturing process which can handle such features is the photopolymerization process, or namely the stereolithography process.
Control of a new phase in 3D printing, where more.
And in this example, they are using a laser, a very low power laser underneath. And while this laser is moving around, it actually cures this photopolymer and makes it solidified.
Of these 3D printed parts will be used in end part production, specifically in mass customization. In a traditional sense, we were only allowed to do
Very interesting.
every single.
Rethink the entire manufacturing strategy.
You see the details, and these are not easy actually to do with other manufacturing processes. Even they may have some colors. The only thing is that they need to put some color pigments into the photopolymer so that the resulting fabrication will be in different colors. Okay, let's go back to, instead of actually going back to the slides, I may continue with the printer. So this is, let me make it larger for you. Any questions, guys, while I'm arranging this camera?
Hocam bazı materyalleri mi toksik yoksa genel olarak mı toksik?
Some of them, they use some special chemicals. They might be toxic. So I think you see the printer here right now. This is a stereolithography process, and you make use of resins. And inside there's a tank here. I cannot open this, let's say, door, since, as you know, the materials are light sensitive. If you open it, then some portion of the material will be solidified and your resulting product will not be successful. So that's why the process is performed under such a special closure. As you see, the color is a bit different, and this actually eliminates such lights going inside the printer, and it will not be solidified once you have such a casing around your printing volume. And again, the principles are the same. We have such a building plate, and the process is actually performed upside down, as opposed to the triple F. In a triple F, what we do, we print the products in this manner. We start from the first layer and then go down. Since our extruder is at the top side, we do the printing in this manner. But things are reversed in this version of stereotypography. And what we do, we start again at the bottom, but this time our wheel table is going upwards. And you see some steps are performed actually at each layer. Right now, we have a laser underneath and it is curing. And then after each layer is completed, we have a kind of sweeper. It sweeps the photopolymers on the table so that there is no bubbles around and the part does not stick to the table. And then after sweeping, it goes up and then goes down. And next layer is right now is being cured with the help of the laser underneath. This laser is just scanning the whole slice and trying to solidify this liquid material, this liquid resin. And I'm using a white one, but you may also have some colorful ones, have clear ones or tough ones. There are many options. You can have flexible material, tough material, is up to you. And at the back side of this printer, they have such a tank. And this is, as you see, a clear material. Depending on your needs, as I said, you can use different tanks. What I do, I simply remove it and then put this one backside. And then underneath of this tank, there's an opening and there's a kind of a gate there. It sometimes open this gate and let actually this resin go into the tank. And sometimes, for most of the time, the gate is closed. The resin inside this tank actually cannot go into the tank. So this is how they handle the material. And obviously, before using, you need to do some shaking so that you have homogeneous material inside. Otherwise, some parts might be just have little polymers. Some part might have some water. So that's why before using it, it's better you do some shaking and try to homogenize the photopolymers inside. And the rest are not that complicated. We don't have any X or Y axis in this one, or just table is or wheel plate. This one is called a wheel plate, and it's moving upwards and downwards. So what happens, how we do the scanning in XY direction? And this is simply done with the laser. And another issue is that they are not moving the laser all the time. What they do is that they have a kind of an lightweight mirror. They reflect the laser on that mirror and they just orient this mirror. By simply orienting this mirror, they can scan the whole XY plane instead of moving the laser underneath. Why do you think they have such an approach? Why they not move the laser and just rotate the mirror?
It's lighter.
Yes, it's lighter. So what is the advantage of having a light thing?
It requires less torque.
Less torque, so it's much faster. So if you want to actually move, let's say, assume that this is a laser. If you are going to move it underneath in X and Y, on the X and Y plane, this will take lots of time. You need to provide more energy. But if you simply rotate a very lightweight mirror, you can do it in a shorter time. It's much cheaper. It's more accurate. So that's why people prefer to use mirrors for the movement of the laser. It's a kind of a light, so mirror is a good choice. We can make use of this property and try to make things simpler. And another issue, like this is a user interface, not complicated. It's right now connected to my computer through Wi-Fi, so I can continue to check the status of the print. Even I can check it at home. Sometimes try to stop it, but you don't have much control over Wi-Fi. You can only stop the print or see the status of your print. For instance, right now it says that 16 minutes is remaining, and can see the part you are printing here. It's a kind of an ornament. I will show you now on the CAM software. And I think that's all what I can say for this printer right now. And if you have questions, you can ask. Otherwise, I will switch to the CAM software. So any questions, guys?
Hocam parçayı çıkartırken sıvı tanka geri mi doluyor?
Yes, the tank is always underneath and it's stationary. As you see, it's just moving in X direction. And it's done for just cleaning the bottom of the table, bottom of this tank. But it does another motion. And as you said, while this one is going upwards, once the print is done, this table, this wheel plate will go upwards, and then I will wait, for instance, for 5 minutes so that all the materials will be going down into the vat, into this tank. And then later, I will take that part, but it's still not finished. I need to do 2 more post-processing. The first one is washing. I will be washing the part in isopropyl alcohol. It's IPA. It's also abbreviated as IPA, isopropyl alcohol. And with the help of that alcohol, we will be cleaning actually the uncured resin around the part. In a moment, I think in 15 minutes, you will see that the part will not be completed. We will have some liquid material all around. So that's why we need to do some cleaning first by using an alcohol. It will be done actually, you can wash it in just 10 minutes. I have a special machine, maybe if you have time, I can show it to you. And then after you clean it, the second step is to do post-curing. Since this laser itself is not enough for curing the material completely, so what we do, we put it into a curing oven, a very simple one. Again, if you have time, I may show it to you to the end of the lecture. Once you do the post-curing, let's say it takes about 30 minutes, and you need to do curing usually around 60 degrees, and then you will be done with the fabrication. Your part will be ready to use. Its strength will be good enough, and you can use it in your desired application. Any other questions?
Hocam
is there any
Özür dilerim.
Hocam,
Ben sonra sorayım.
is there any application where more than 1 mirror is used?
Yes, you can use more than 1 mirror if you have 2 lasers. For instance, the professional SLA type of printers are very large ones, and you cannot handle it with a single laser. So what they do, they have multiple lasers, usually around 4 of them. So one laser is responsible for one quadrant, and the other one is responsible for the other quadrant. So in such cases, you may have more than 1 mirror. But if your question is using 1 laser and 2 mirrors, and I don't know, but that might be a research idea. So that I think with the help of 2 mirrors, you may do printing on 2 sides of the table, right? But you need to be careful about it, since the power of the laser might not be enough. But it's a nice idea, I guess. You may do some check whether anyone is trying to do such a thing or not.
Hocam, is it okay if we just put the part to curing in the sun? Like outside?
If you wait long enough, let's say for 4 hours, 5 hours, I think it might be okay. You don't need to have a special oven.
Also, what do you do with the rest of the resin? Do you like store it, or do you leave it there for the next print?
Yeah, this is a bit dirty process, I usually call it. I don't need to take this one out. I usually keep it there. And then if I want to use a different material, what I do, I get another tank, another empty tank. So for each material, I prefer to use a separate tank. Separate, let's say, they call it as vat. For each material, I have a separate vat. Otherwise, it will be quite complicated, since what you need to do, you need to get this material and put it into a kind of another tank, store it somewhere, and then clean your vat properly, and then pour new material. So in order to solve this problem, what I do is to use a new vat for each material. Any other questions, guys?
Hocam ben de şeyi soracaktım. 2 tane sorum var da. Birincisi bu yaptığımız şeyde infill structure yapıyor muyuz? FDM'de olduğu gibi. Ya da bir de support structure'a neden gerek var? Onu tam anlayamadım ben.
Yeah, I will show you now in the CAM software. You may ask your question related to the machine, but the question about the CAM software I will answer in a moment.
Tamam, sağ olun.
Any questions related to the machine, guys? And it's about this SLA printer. So I will try to be in that position and show you the, yes, this is much better. Now let me share you the CAM software. Yes, this is the CAM software of Formlabs 3D printers, SLA printers, and I think it should be free. If you are interested, you can download it. And I already imported an STL file here. And as you see, this is a quite large one. And like in the CAM software of FFF, you can do some scaling, for instance, here. Let me first select it. And then I think I did it to 0.3. Yes. This is now scaled. And you can do some orientation. You can rotate it. It's up to you. Here you can add some support structure, or it may be generated in an automated manner like in the FFF case. You may adjust some properties of support structures like the thickness of your support. So there are some critical issues. I will show you them in a moment. And what is that? And this one is about for laying out. Let me switch to this view. Oops. Yes. So this is our part now. They have another nice feature. If you just click this magic button, let's say, it orients it properly, generates support structure. So for, let's say, first users, if it's your first time, or let's say your initial experience with the printer or the process, it's better you use this tool. So let's do the same one-click print. Now with the help of this, it will set up the print. Now it's calculating the best orientation. Now generating the supports. So there was a question about why do we need to have support. The question is the same again. If you are printing, you cannot print material on air. Since we have liquid material here, and with the help of the laser, we are solidifying. And if you solidify in air, then obviously your material will not be able to keep its position. So that's why we need to have some support structures. So you see, we have a different type of support structures. They are kind of like trees. And the thing is that if you look at this part, they have a thicker portion, but the parts actually they are connecting with the part is a bit thinner. The reason is that once you have such thinner parts, then it will be easier to break with hand or with some mechanical equipment. But if you have thicker parts here, then there will be a solid connection between the support structure and your part, and you may not be able to break it. So that's why people prefer to use such thinner parts at the connection points. Another thing, let's focus on yes, you see how the part is fabricated. And another nice feature of this SLA printer is that they kind of have a raft here. If you don't have this raft, then at the end of the printing process, it will be quite difficult to remove it from the build plate. I had these difficulties. If you do not print your part right, if you do print your part right on the build plate, then it will be quite sticky and you will not be able to remove it from the plate. And that's why we prefer to have such a raft underneath. And this has some angles here, and it becomes easier to remove with a kind of a knife, and things becomes much simpler. Now you see that we have the support structures started to be built. Another nice feature is that they print the name of your STL file on this periphery. As you see, it's written spiral, spiral, spiral. Not seen here. Let me. Yes. Spiral, spiral, spiral. So name of the STL file is on this periphery. It's a nice feature. And right now I'm on the top view. The support structures are generated, as you see. Yes, let me switch to the other view. This part is actually the thing we want to build. So that's why it's in blue color, but the support structures are in orange. And I said that the parts, the support structures are connecting to the original, let's say, model has a smaller radius, so that after the parts are finished, you can easily remove them. Let's focus on here, for instance. The thickness is reduced, the radius of the support region is reduced, and at some point, as you see, we start building the real model we want to have after the fabrication.
Hocam bir şey sorabilir miyim? Tam
Yes,
burada. Hocam sanki burada şu angle'lar 45 dereceden fazla değil mi build angle'ları?
Yes, this one, you can even print some parts having, let's say, 70 degrees. We have much more freedom in this technology. Not 45 degrees, not our limit. You may even try more degrees.
Anladım hocam, teşekkür ederim.
Another question was about the interior, and in these parts, we cannot have voids or porous structures. The interior should be completely filled with material, and that's why this laser is always scanning the contour completely. We cannot have any gaps, or we don't have any, let's say, different infill patterns. The interior should always be completely filled with the material. And if you look at the details of this contour, what our laser is doing is that it has 3 shells. As you see here, 2 of these shells have very little gap between, and the other one has a bit more gap between the other shells. But the thing is that, once again, we need to fill the interior completely with material. The parts you are building with SLA or other photopolymerization based processes, we should always have solids. We cannot have voids inside. We cannot have different infill patterns. They should always be completely filled.
Hocam, can I ask a question?
Sure.
If we assure that the resin can pour out, can we use infills? For example, by building chambers and keeping a hole so we can drain the part after the process is over?
Yes, you can do that, and but you need to be careful. The software is not actually allowing you to do that, but if you are printing or designing a custom machine, you can do that. Another issue is that you should be actually washing it properly. You shouldn't have any uncured resin inside. And now the part is finished, is about to finish. I am sorry. That's why I stopped sharing the CAM software. It says that just we have 1 minute remaining. In a moment, I think we will see the printed product. Yes, now as you see, it's going upwards. The part is finished. Let me move the camera maybe closer, but I need to do some position backside. So let me zoom in. So this is maximum I can go right now. And this part is there over there. And as you see, we have liquid all over there. So that's why I will wait for about 5 minutes or 10 minutes and then do the second process, which is about washing. We will be washing it with IPA. And then after washing is complete, I can do post-curing operation. Any questions, guys, about the prints?
Hocam, solidification process geri döndürülebilir bir şey mi bu lazerle solidify ettiğimiz zaman?
I will be talking about it. We are using thermoset materials. Thermosets are not recyclable. You cannot, since you start with liquid, you do solidification, and you cannot go back to the initial state. So that's why this is not recyclable. But as you know, in FFF, in fused filament fabrication, we can easily do recycling since we are using thermoplastics instead of thermoset materials. This is another difference with respect to the FFF type of printers. Any questions, guys? Now I will switch to the CAM software and try to complete. So this is how we do the fabrication. The blue ones are the parts, actually the real part we want to have. And as you see, since it's a bit complicated product, inside the part we have extra support structures. So this is quite problematic. After the part is printed, we need to do some support removing operation. And this will, I think, take lots of time. So I may keep it as it is and use it as a tool in teaching SLA process. But this actually how the printer fabricated the part. These are the layers. You see some support structures and the actual part. Any questions, guys?
Hocam bu parçayı şu an bu gördüğümüz şekilde sağa yatırarak build edemez miyiz? Yani niye yan yatırılmış şekilde yapıyoruz bunu?
We can do that. This is just the result of the magic tool. But as you mentioned, I prefer to print it in this orientation. That will be much better. But let's see. In this orientation, I want this software generate some support structures, auto generate all. Let's see if this one requires some support structure inside or not. During this time, if you have questions, you may ask.
Hocam en alttan değil de parçanın içinden yine parçaya çıkan support structure'da yapabiliyor mu?
Yep. As you see here, I think this one is your answer, right? So since it's a difficult product, we cannot eliminate use of support structures. Regardless of the orientation, we will always have support structure. Otherwise, the quality of your part will be less. And let's try to have no support structure, okay? And then I want to show you another property of it. Let's switch to top view. As far as I remember, it should be showing some regions of, no, not showing. Sometimes it's warning critical regions where we need to have support structures. But I think without using any support structures, we may be able to print it. Since, as you see, while we are going upwards, we don't have any dramatical changes. The changes are little. We are just shifting the layers, maybe some little millimeters, some millimeters. So I may print it without using any support. But according to the software, it says that you need to use support structures. But you can take the risk, print it without any support structure and see the result. So it's up to you. You don't need to always use the settings, the default settings, the default support structures. You have your freedom. You can print without any support structures. I think I already answered the questions on the chat area, right? Yes, the things we mentioned, we discussed all these questions. So what is time? We have 15 minutes, so I can continue with the slides and then have the quiz later, okay? Any questions, guys, before I switch to the slides? Do you have questions regarding the CAM software and the printer?
Hocam bu parça ne kadar sürede basıldı?
About, I think, 1.5 hour maybe.
Yani şeye göre daha mı hızlı daha mı yavaş FFF'lere göre?
Somehow similar. I think yes, it's shown here in this orientation. If you print it in the vertical orientation, it will take about 1 hour and 45 minutes. You see here, printing time 1 hour 45 minutes. And what was the dimension? I forgot the dimension of it. Since we have done some scaling, let's see the dimension. The height is 32 millimeters. You can check it on your printer. It's about 3 centimeters. Probably in Cura, it may take about the same time, since the resolution, right now, the layer thickness is 0.1. And in SLA, in this printer, we can only decrease it to 50 micrometers, which is actually much better than triple F, since if you remember, in Cura, we have about, I think, in minimum 60 micrometers, and this is not actually usually preferred. We prefer to have in minimum usually around 100 micrometers, but since in SLA, we can print small products, small features easily, so you can set it to 50 micrometers and do your print. And let's see, if we set it to 50 micrometers, what will be the printing time? You see now it's doubled. Initially, it was 1 hour 45 minutes. Now, if you decrease the layer thickness to the half, the printing time will be doubled.
Hocam bir de %100 dolulukla oluyor demiştiniz de içini boş yapıp içindeki reçineyi de boşaltabiliyoruz değil mi? Öyle bir şey de vardı sanki.
But you should do it in your design. You should design the same part by using just shells in your CAD tool, and then later import that STL file into here. You cannot do it right on the CAM software. You should do it in advance. But the problem is that it will be quite difficult to remove that resin inside of your part.
Hocam bir şey sorabilir miyim?
Yes.
Kaçırdım galiba ben ama bundan sonra yaptığınız washing proses diye bahsettiğiniz şeyde amaç neydi tam olarak?
We have liquid inside here. Not inside, but let me stop sharing. I cannot take this one out right now. Oh, let me do it. Yes. Yeah, this is the result. So I can simply say that the printing is not finished. You see we have bubbles here. Even inside the part, we have some material. So I need to get rid of this resin. And how am I going to do it? I will do it by using IPA, isopropyl alcohol, and with the help of in 10 minutes, we will have a clean part.